All right. So again, today's do now question says, why do different types of elements or atoms need to gain or lose valence electrons? So Brighton pointed out that metals lose their valence electrons and non-metals gain more valence electrons. John said it was to become more stable in order to become balanced. Good. Good, Anaya. So the atom's orbits can be full, which is what makes them stable. Very good. Good, good, good. So good, that's in the right direction, right? In general, atoms want to have a full electron orbital, circle, ring, whatever you want to call it, all the same words. And so they're going to do whatever is easiest. And that's either to just get rid of a few electrons or to just gain a few. And that depends on how many they have in that outer orbit or ring to start with. And so they're going to gain or lose valence electrons until they become stable. All right, so we're going to play a Kahoot review now because we have actually, in a very short amount of time, learned and figured out a lot of content. And so to make sure we're all on the same page here, we are going to play this Kahoot. And so on your Chromebook, your device, or your phone or tablet, if you could log in, and then we will play once everyone is in. All right, is there anyone else we're waiting for? like charges do? Good, like charges repel. What about opposite charges? Good, opposite charges attract. When opposite charges are closer, their attraction is stronger. Very good. When opposite charges are further apart, their attraction is weaker. When like charges are closer, what happens? Their repulsion is stronger. All right, good. What about when like charges are further apart? What will happen? Good. The repulsion is weaker. What is an atom? Basic unit of matter. Which of the following is not a subatomic particle in an atom? Good. We do not have electricians in atoms. That would be correct. Which of the following is true about a proton? Good. So they have a mass of 1. Remember, they have a positive charge, okay, +1 charge. What's true about a neutron? Good. So neutrons are neutral. They have also a mass of 1 atomic mass unit. What's true about electrons? Good. So electrons' mass, if you remember, is so small we don't really count it. So we just say they have no mass and they have a -1 charge. Which of the following is not located in the nucleus? Good. Electrons, right? They orbit around the nucleus. Which parts of an atom are attracted to each other? Good. Protons and electrons, right? Because they have opposite charges, so they attract. Electrons closer to the nucleus take more energy to remove, right? Because they're closer to the protons, so there's a stronger attraction there. What about electrons that are further away from the nucleus? Good. So since they're further away from the protons, that attraction is weaker, so it doesn't take as much energy to remove them. How many electrons can go in the innermost ring of an atom? Good. 2. How many electrons can go in any other ring past the innermost ring? Good. 8. What's a valence electron? Good. Outermost electron. What information in the periodic table tells us the number of valence electrons an atom has? column number. Which of the following groups of elements would not lose their electrons? Right, so this was a tricky one to remember. So remember, groups 1 through 3 lose all their valence electrons to become stable. What type of elements lose their valence electrons? Good, metals. So it's the stuff again on the left-hand side of the periodic table. Which of the following groups of elements would not gain electrons? Good, group 2 elements. And this is because, right, groups 5, 6, and 7 would gain electrons to become stable. What type of elements gain valence electrons? Good, non-metals, the ones on the right-hand side of the periodic table. Which is true about group 8 elements? Good, they do not react at all. Which of the following would be more reactive? All right, this was a tricky one. So remember, groups 1, 2, and 3 want to lose their valence electrons to become more stable. The easier it is for them to lose their valence electrons, the more reactive they are. So first, if they have fewer valence electrons, that makes them more reactive. Then if they're bigger, that makes them more reactive because there's a very, very weak attraction between the electrons and protons. And so they're very easy to get rid of. Very good. Now, which of the following would be more reactive? Okay, group 1 elements. So again, if I have fewer valence electrons, it's easier for me to get rid of my valence electrons, which makes me more reactive. So group 1 element, right, has only one valence electron. Which of the following would be more reactive? Ooh. Okay, so these are tricky, right? Now on the opposite side of the periodic table, I have to kind of flip or reverse my thinking. On the right-hand side, groups 5 through 7, they're trying to gain or attract more valence electrons to become stable. So on the right-hand side of the periodic table, the easier it is for them to attract valence electrons, the more reactive they are. So for an atom to more easily attract electrons, I would want it to be closer to the nucleus where the protons are, so that attraction is strong. So a smaller atom, which has very few rings, means that the electrons get pulled real fast toward the protons. So those small atoms gain electrons more easily. A big beefy atom on that side of the periodic table, there is such a long distance between the nucleus where the protons are and the electrons it's attracting that attraction is weak. Okay, so a weaker attraction for the nonmetals is going to mean less reactive. Okay, so this is kind of the opposite of what we just thought of for the metals. All right, one last one. Which would be more reactive? Okay, so again, opposite thinking of the metals, right? So we want them to be small, but we don't want to think we have few to get rid of. Now we want just a few to gain, right? So a group 6 element has to gain 2 valence electrons, where a group 7 element has to only gain 1, right, to get to 8. And so that makes it more reactive. Less valence electrons to have to gain to become stable makes it more reactive. So, kind of the pattern here when I think about it, right, is the less work the atom has to do, the more reactive it is. Okay. Very good, very good. All right, good job, everybody. Oh, nice, Ariana and Sydney, runner-up. Very good, very good. All righty. So your homework last week then was the 11.12 practice. Okay, it was a series of questions here, and it's decently long, okay? So I would like us to go over some of these today, okay? And then we will go over the rest of them in another class period, okay? So again, anytime you need to access old homework assignments when we're going over them, if you just go to your Google Drive and search for the title, you'll find it. And then you can open it up, kind of make corrections or ask questions as you notice things. All right. So let's see here. We actually just answered number 1 through 12. Number 1 through 12 come directly from the notes that go with this, and we just answered those in the Kahoot. So I'm actually going to skip over that. Okay. So number 13 says, how many valence electrons do sodium, potassium, and rubidium have? Number 13, how many valence electrons? 1, good job. And we know that, right, because they are in group 1. The notes have the same title as the practice. Okay, so they're in group 1, so they have 1 valence electron. So number 14, would they gain or lose valence electrons to become stable? They lose, good. And how many would they lose? 1, okay, very good. All right, number 16, how many valence electrons do beryllium, magnesium, and calcium have? Good, 2 valence electrons because they're in the second column or group 2. Would beryllium, magnesium, and calcium gain or lose their valence electrons? They would lose. So in total, they would lose how many? 2. All right, good. Number 19. How many valence electrons do boron, aluminum, and gallium have? 3. Would they gain or lose their valence electrons? Lose. So they would lose how many total again? 3. Very good. What's unique about carbon, silicone, and tin? Very good, Sydney. They could gain or lose valence electrons. They're in group 4. So it is equally as easy to lose all 4 valence electrons as it is to gain 4 more to become stable. And remember, when we're talking about these numbers, and some of you are sitting here like, why do we have to lose or gain that many? Well, remember, we need the outermost shell to be stable. So that means, right, if they have a big outer shell that can hold up to 8, I either need to get rid of everything in that shell, so the next one underneath it is full, or I need to fill it up with more valence electrons to equal 8. Right, 23, how many valence electrons do nitrogen, phosphorus, and bismuth have? 5, very good. Do they gain or lose? Gain, and how many would they gain? 3. Okay, so let's make sure we understand why, right? We need that outer ring to have 8 valence electrons to be stable. So if it currently has 5, we have to think, how many more do I need to equal 8? That would be 3. All right, number 26, how many valence electrons do oxygen, sulfur, and polonium have? 6, very good. Would these elements gain or lose electrons? Good, Kobe, they would gain. And number 28, so how many more would they gain to become stable? 2, right? Because 6 that they already have plus 2 additional would equal 8 to be stable. 29, how many valence electrons do fluorine, chlorine, and bromine have? 7. How would they have to gain or lose electrons? They have to gain. Very good. And how many do they have to gain to become stable? 1. Very good. Right, because 7 plus 1 will give us 8. Number 32, what is unique about neon, argon, and krypton? They're already stable, right? That's why they don't react. They have 8 valence electrons. They have a full outer orbit or shell or ring or whatever the heck you want to call it. And so they don't react with things. All right, very good. So again, when I use my logic here for these next questions, we are going to refer to the periodic table at the top. So it would have been a lot of flipping back and forth in your periodic table, right? Because we have to use that to get these answers. They don't just come out of thin air, okay? So we need to get used to using our periodic table. So I want to order these from most to least reactive. Most to least reactive. All right, good. So we would order these. Cesium would be the most reactive, then potassium, then lithium. Why is cesium the most reactive of this group? Why is cesium the most reactive of this group? Okay, so one, it's lower down in the column or group in the periodic table. Very good. If it's lower down, what does that mean about the size of cesium?
That the mass is higher.
The mass is higher, and if the mass is higher, cesium must be what? Big or small?
Bigger.
Very good. It must be bigger. And so remember, for our metals, the bigger the atom is, the easier it is to get rid of their valence electrons because there's that weak attraction. So cesium is the biggest, so it's the easiest to get rid of its valence electron, which makes it the most reactive. All right, now let's look at number 35 and 36. We have magnesium, aluminum, and sodium. What order would I put these in from most to least reactive? You are close, Kobe, but that is not correct. Most to least reactive. Not quite cushy. So which of these three has to do the least amount of work to get rid of their valence electrons? Okay, so how many valence electrons does magnesium have? 2. Good, Ayana. Is there any element there that has less valence electrons? Sodium, very good, John. So which is easier to get rid of, 1 valence electron or 2? 1, okay? So sodium is the most reactive, then magnesium, and aluminum is the least reactive because it has the most valence electrons to have to get rid of. All right, number 37. So now we're going to look at some nonmetals. List these from most to least reactive. Remember, nonmetals, we have to think opposite. Number 37, how would I list these? Very good, Cushy. So Kush said nitrogen is the most reactive, then arsenic, and then bismuth, which is correct. Why is nitrogen the most reactive in this group? Remember, we need to think opposite of the metals. Why is nitrogen the most reactive?
Because the column.
Because it's what? Why is nitrogen the most reactive? Ah, very good, very good. So that's what Kobe said. Kobe said it's placement in the column. So first, yes, if it's at the top, that means it has a smaller mass. And then what John is getting at here is if it has a smaller mass, that means the atom is smaller. A smaller atom means that there's going to be a stronger attraction from the nucleus to any electrons it's pulling in. So on the non-metal side, if atoms are smaller, they are more reactive because they more strongly attract or gain valence electrons. Okay, so we just had to sequence them here from smallest to largest, which is opposite of our metals. All right, number 39. Whew. Most to least reactive here. Okay, very good. So John noticed, right, that radon is a group 8 element, right, which means what? Non-reactive. So radon should be at the very end, okay? Least reactive. Okay, so we got rid of one. Okay, now what else can I look at here? Let's stick to the right-hand side of the periodic table, okay? Right, so we're on the right-hand side. I've got astatine, polonium, sulfur, and fluorine. So let's look at polonium and astatine. Which of those two is more reactive? Polonium and astatine. They're in the bottom right corner of the periodic table. Polonium and astatine. Which is more reactive? Which of them has to do less work to gain valence electrons to become stable? Polonium or astatine? Ah, good, Sydney, polonium. So polonium is a group 6 element. So that means it has 6 valence electrons. It only needs to gain 2 to become stable. Actually, it should be opposite, Sydney. Astatine then is a group 7 element, which means it only has to gain how many? From group 7, how many valence electrons do I have to gain to become stable? 1, okay? So astatine is more reactive than polonium because astatine needs to gain fewer valence electrons than polonium. Okay, baby steps here. And so this is how, right, if I was doing this as a homework assignment, this is how I would be thinking it out loud. You know, I would kind of just grab a couple elements and try to see which of those two is more or less reactive. And I would keep pairing them together until I had a sequence. Okay, so sulfur and fluorine. Would sulfur and fluorine be more or less reactive than these 3 elements we already have lined up? Would sulfur and fluorine be more or less reactive than the 3 elements we already have lined up? Would sulfur and fluorine be more or less reactive than the 3 that we have lined up? Good. Fluorine and sulfur would be more reactive. Why are they more reactive? Why are sulfur and fluorine more reactive than astatine, polonium, or radon? So there's one key word in what John said. John said fluorine is in group 7 and it only has to gain one valence electron and it's smaller. So fluorine and sulfur are smaller than astatine, polonium, and radon. So remember, if a nonmetal is smaller, that means it more easily attracts the valence electrons. And then that's how we figure out between sulfur and fluorine. So fluorine is the most reactive because it is the smallest and has the fewest number of valence electrons to gain. Then it would be sulfur, and then it would be astatine, polonium, and radon. Okay, that was a tricky one, right? But you can see if we just take the time, you can problem solve through that, but it does take some time and effort. Okay. So before we move on real quickly, I do just kind of want to sketch something out to make sure that we understand here. Per usual, I'm going to be drawing on my computer, which means that the images are going to be not awesome. Right, so we know, hello? Oh my goodness, okay. Metals are on the left side of the periodic table. They have to lose their valence electrons, okay? And we know that they are more reactive if they have fewer valence electrons and if they are larger, okay? And so again, let's take a second and just make sure we understand why this is, okay? So if I have an atom, and we're gonna say, right, I've got my protons, too many. I know I've got neutrons in the nucleus. Okay, and then I gotta draw electrons. So if I have 5 protons, then I'll have 5 electrons, right? How many electrons go in the innermost ring? Good, 2. I'll just represent them as an E. And if I have 2 there, how many then have to go on the outside? For this atom in particular, I have to get up to 5. So how many does it have in the outer ring? 3, good. Okay, let's remind ourselves why, right? If it has fewer valence electrons, easier to get rid of them. If it's larger, well, I wanted this to be red. Oh my gosh. There we go. Okay, the greater this distance is, means weaker attraction. If there's a weaker attraction, it's easier to get rid of the valence electrons. And if it's easier to get rid of the valence electrons, it is more reactive. Okay, now let's do the same type of processing for the nonmetals. Okay, and just to remind you guys, I do record all my teaching now. So you can just access that from the daily plans. It typically takes about a day and a half for me to get it linked. So like today's lesson will not be linked in like a half hour, an hour. But by the time though, tomorrow night though, it will be linked. All right, so nonmetals. We know that they are on the right side of the periodic table. We know that they have to gain more valence electrons to become stable. And for nonmetals, they are more reactive when they have fewer valence electrons to gain and when they are smaller. Okay. So we're going to do the same thing again where we're going to draw, let's see, we'll do fluorine, okay? So fluorine has 9, so you need 1, 2, 3, 4, 5, 6, 7, 8, 9 protons. Those are my neutrons in the nucleus again. And now I am going to draw my electrons. So like we just said in the last one, I put 2 electrons in the innermost ring. I need to get up to 9 total. So how many electrons go in the next ring for this atom? I need to get up to, very good, Kobe, 7. And remember, they kind of pair up 20. All right, so now what are we talking about here with size? Well, it's the exact opposite of what we just talked about with the metals. So in a nonmetal, if this distance is smaller, that means the attraction is stronger. This is attraction. The attraction is stronger, then it's easier to gain valence electrons. And if it's easier to gain valence electrons for this group, because that's what they're trying to do, gain valence electrons, that makes them more reactive. Okay. So again, I just wanted to go back over this to make sure we understood it. I can also put pictures of this in our daily plan slides. All right. So now in Canvas, if you can click to 12.3, bond observations, homework. So it says, now that we've learned about what makes atoms stable and not stable and what atoms need to do to become stable, let's explore atoms, valence electrons, and stability further by looking at bonds. Okay, so I'm going to click on the assignment, just like you would to open it up. I got a copy of the periodic table at the top for us to use. And we've done something like this before. So in this one, you have not learned about these bonds yet. Well, what you're going to do is look at the pictures I'm giving you to try to learn information about them. So it says here, how many valence electrons does sodium have? And I tell you, you have to look at the periodic table. Would sodium need to gain or lose valence electrons? So a little bit of review information. And then it's going to start connecting to the picture. So we're using information we've already learned, and we're trying to apply and connect it to new things that we see in these diagrams to answer the questions. So you have one diagram, here's a second diagram, a third, and a fourth, okay? So you can see you have 22 questions total. It's not bad at all, okay? You're gonna use the about 15 minutes left of class today to get started on this. And then whatever you do not finish today is going to be homework, and this assignment again is due tomorrow night, okay? Does anyone have a question about this assignment? All right. If you have any questions, once you start working on it, make sure you email me tonight and tomorrow to let me know so I can help you. Otherwise, you have the remainder of the time today to get started. If it works better for your Wi-Fi, because I know Wi-Fi in different parts of the school building or at home might be spotty, to log out of Zoom so that you can work on this assignment in Canvas, I am perfectly fine if that's what you need to do. Okay. Then I will see you guys on Wednesday. Again, make sure you let me know if you have any questions or problems. I just want to eat my lunch.